Here? Okay, everybody. All right, good. Okay, our speaker today is Lockwood Carlson. He comes highly recommended as a speaker. He has a PhD in theoretical physics from the University of Wyoming. He's done research at the University of Wyoming and Princeton University. He's held the Renier Chair in Technological Leadership from the University of Minnesota. And he, early on, a number of years ago, he published some books. Don't Sweat the Small Stuff, and it's all small stuff. You remember that one?
No.
No?
I don't remember that.
Okay, not you?
I don't think so.
Okay, I got it off the web, and it looked like it was yours. You can't trust that web. Okay.
The Russians are hacking me.
It's what?
The Russians are hacking me.
The Russians did it. Okay. Okay. The topic is going to be climate science and global climate change. How many here think that global warming is happening? Okay, you got a good audience. Okay. 72% of the registered voters say yes, and 79% think that children should be taught causes and potential solutions for climate change. Today's topic is timely, of course, because of what's been happening in the administration. We have a number of deniers that are calling the shots right now, and so we need to speak up and make sure our voice gets heard, that it's real, and like it or not, we're going to have to deal with it. Dr. Lockwood will present the scientific basis to help understand the changes in the last few hundred years. What effect CO2 has on those changes, and what effect economic and policy issues for us and all other nations is. Technical difficulty here. Doesn't want to come apart. More importantly, though, I think some promising technologies and geographical trends like Arizona will be actually hotter. And so we're looking at a hotter desert than we've had before, and at least that's a projection. And there's going to be these kinds of changes all over the world where some people that were colder are going to be hotter or even colder, and they'll have a lot more rain or they won't get the rain. So it's a change that we're looking at, and it's going to be a major impact, I think, on society. So give it up for Lockwood Carlson.
Thank you. Thank you, Jerry. Okay. My name's Lockwood Carlson. I am a physicist. That's a total description of who I am. I have a God. The answer to that is I'm a physicist. And that's where my God lies. My son is also a physicist, and one of my daughters is a physicist. Go figure. And my son worked in sophisticated computer programs that solve differential equations. And he got involved with weather and climate modeling. And back in the 80s, late 80s, early 90s, I asked him, I hear a lot about this climate situation, and what do you think? And he says, well, it's definitely, the globe is warming, is confirmed, and so forth. I was busy in a career, so I was doing other things in physics. Around 10 years later, I says, okay, it's warming, I can see that. Is it anthropogenic? Is it we that are causing it, or if that's a well-posed question? And he said, yes. And so he's very conservative in terms of getting all the data in line before he'd make a statement like that. So when I retired, I figured, let's get into this. I have a background in how light scatters in atmospheres, light and infrared and so forth, and also a background in massive parallel computing to solve very complex problems. So since then, I've just been kind of hanging on, reading the literature, talking to people, and so forth. This is a data-driven topic today. It's not going to be easy. It's not simple. I'm not going to make it simple because the truth is complex. This type of science is a different kind of science than particle physics and cosmology, which I work in. Much harder, much more complicated. It's more complicated than any other area of the physical sciences that I know of, because the system is so diverse and complicated itself. In other words, the Earth as it sits in the solar system. So it's not going to be easy. I'm going to show a lot of graphs. If you don't like graphs, I'm going to try and verbalize the bottom line for these graphs. And you may not have time to see what's X, what's Y, how are things going. But those of you that like graphs are going to probably have a good old time. Public fora, such as television, websites, blogs, cable, newspapers, and so forth, are almost always, when they say something about climate and climate change, they're almost always wrong or misunderstanding the situation. Be very, very careful. And this is mainly due to the fact that it's a complex subject. And when scientists publish a paper and they want to get some more money for next time, next funding round, they'll put some headlines on papers or in popular media that really misrepresent the actual status of where the science is, what they have done, where they want to go next. So basically what I'm saying is be very skeptical of anything you see coming over the media. It doesn't leave a lot of options. You could read the refereed literature, but that takes time and it takes a background. Or you can find a friend who does have a little more domain expertise in some areas, or find a public figure that you learn to trust and you develop credibility with on this particular topic. So ignore headlines. My goal is to really give you appreciation for this complicated science, this complex science. Appreciation for where it's at, the incredible knowledge and explanatory power of the science that's already been done on understanding our climates, our planet's climate over the last, say, 3 or 4 billion years. It's truly remarkable, the strides that have been made in the last 100 years, but most importantly in the last 10 or 15 years and so forth. Looming all over this is that this is a serious topic affecting everyone in this room, every person on the planet, children, grandchildren, for several generations to come. The time scales involved and what we're looking at today for things that humanity may want to do something about, the time scales are hundreds of years, some few thousand years, in terms of what we do in the next 100 or 200 years. This is a problem the likes of which human society has never had any experience with. And to say that governance may be an issue is stating the obvious. There are going to be no short, easy answers. I'm not going to gain your support by showing you a lonely polar bear. I am not a catastrophist. I'm an optimist. And I'm going to finish with things that are looking up. And the things that are going to bring us through this are the things that got us to where we are today as a society in terms of those good things that we secular humanists value. This is our system. I'm going to be talking about a system, and it's really the atmosphere, the oceans, large lakes, land, and the cryosphere, places where there's water that's below 0 Celsius. So could be snow, ice caps, glaciers, whatever. And we're going to take a quick look, a quick drive through 1, 2, 3, and 4, each of which is worth a full semester course in a university setting. So let's start with the atmosphere. That thin skin of 10 or 20 miles above the surface of the planet, which is just like thinner than a skin on an onion. But first, let's look at other planets to look at the effects of atmospheres. People say, well, we only have one planet and it's an experiment. We can't, we have that great limitation. Well, we have other planets, so we know a lot about. Venus is closer to the sun, but hardly any sunlight gets to its surface. It's quite dark, and it has a temperature typically of 477 Celsius. If you want to cook a pizza in 5 seconds, that'll do it for you. Without the major component of its atmosphere, carbon dioxide, the temperature would be 46 Celsius cooler or colder. The only reason it's as hot as it is due to the fact that it's got a lot of carbon dioxide in the atmosphere. Mars, not much atmosphere at all, but some. And look at the power of a little bit. The temperature on Mars, let's say, is typically 47 below Celsius, which is around minus 50 degrees Fahrenheit. For those of you from northern Minnesota, you may have experienced that. It has some CO2, and the temperature, if there were no CO2 in the atmosphere, would be 10 Celsius, or around 18 Fahrenheit, cooler. The Earth, if the Earth did not have the CO2 we have, which is a tiny, tiny trace amongst oxygen and nitrogen, if we didn't have that, this would be the average temperature, 18 Celsius negative. Why? It's often called the greenhouse effect. I'm sorry, it's not the effect that makes greenhouses warm and good for growing things. But everybody calls it the greenhouse effect, so we're going to keep calling it that. It is what it is. There's the land, there's the sun. So the sun shines on the Earth, and we have these gases, greenhouse gases, CO2, methane, nitrous oxide, CFCs, and so forth. And we know they're greenhouse gases because we know how they respond. Those molecules respond to infrared radiation. They absorb in certain bands and don't absorb in others. The sun largely goes right through the atmosphere, right to the surface of the Earth. A little diminution, but not very much. It's because it's visible light centered around the green, not a lot of IR. It's in terms of the total power that the sun delivers to the surface. So the surface heats up. It absorbs some of the sun's energy, reflects some of it, and it heats up. Hot things emit infrared radiation. So when you want to see if your house is leaking in the winter in a cold climate, you get a thermal imaging system. You look in the infrared, and you see where the heat is. So that energy, some of that energy that's heating up the surface, will be re-emitted as a glow, which you can't see, but a thermal imager can. It's not a lot of watts per square centimeter, but it's there. That goes into the greenhouse gases. They are active in the infrared. They say, wait a minute, this is not sunlight anymore. This is infrared. And so some of it gets through, but not all of it. What doesn't get through gets mixed up and stays in the atmosphere or goes back to the surface, gets reabsorbed, and you end up, after time, in what's called a steady state equilibrium. If you add more greenhouse gases, duh, you get less getting through and more getting mixed up in the atmosphere and going back and reheating the Earth. And over time, the situation will equilibrate to a temperature that is a little bit warmer than the first example. This has been suspected since a French scientist in the 19th century started speculating about it. It has been a scientific hypothesis in the 19th century, and early in the 20th century it was based on measurement facts, and by Arrhenius, a Swede. So my name's Carlson. This is what our planet would look like. This is a picture of the Earth with no carbon dioxide in the atmosphere. And methane, come see, come saw, wouldn't do that much. In fact, methane would be gone very quickly, within 10 years, if you somehow started this process. So it is our blanket. It is why we are here today. It is why Homo sapiens evolved from earlier species of primates, because the temperature is pretty much Goldilocks for a lot of creatures such as us. This looks complicated, so don't worry about it. I'm going to talk you through it. It's a repetition of what I just said, only with some numbers on it. Sunlight is an incident 340 units of power per square meter. Some of it gets reflected from the clouds right away. Ever see a picture of the Earth? You got a lot of white stuff for clouds. That's this stuff right here. Some of it is absorbed, not much, as I said. Some gets down to the surface, heats it up. Some gets reflected from the surface, and so forth. So now we've got some accounting going, double entry accounting. The surface heats up. It then starts to emit infrared radiation, and there's that number, bigger number than that one. But we do our accounting. That's what gets out into outer space, never to be seen or felt again. Some of it gets down and mixes back with the surface. If you look at these numbers, they all add up. That's because it's not a glorious accident by a creator. It's because the system's at equilibrium. If some of these numbers get out of whack, the whole system readjusts, tunes it up so that energy in equals energy out. But you got to account for heat when you do that. So CO2 is something important. It's important to go back in history so we can understand it. And the best place to start is drilling ice cores in Antarctica, Greenland. And this Vostok is a station in Antarctica. There's a core drill. And in these ice cores, which are go from last year down to several thousand years ago, many thousand years ago, this is compressed snowfall. So it gives you a fresh look at each year, each season, and it just gets stacked just like geology. But in these ice cores, there's bubbles. And those bubbles contain ancient fossilized atmosphere. So whatever the atmosphere was at the time that this particular slice got laid down and compressed and finally converted to ice, the atmosphere is in all those bubbles. You grind it up, you measure the gases, the CO2, and you could do a lot of other things with it. And what do you get? You get not a proxy for CO2, but CO2 direct measurements over time. 800,000 years ago to present, this is a concentration of CO2. And first note, there's very little CO2 in the atmosphere, 300 parts per million. So that's really less than 0.1%. So why are we worried about it? Well, what you can notice here is that first of all, these ups and downs, every 100,000 years or so, those are glaciations. And this is the particular part of the age of our planet where these things happen. Also, you'll note that values hang around 200 to 300 parts per million. And then you go up to the present, and you have this. On this chart, it's a vertical spike because the ink isn't thin enough to show the slope of that rise of CO2. So that's just data. Let's follow through. Well, the first thing I want to ask is, where the hell did this stuff come from? What's going on here? It corresponds to the industrialization era of our society. There's carbon dioxide in a shorthand version. And here's methane. And here's nitrous oxide. So we got a front line for a hockey team. 3 hockey sticks. Those are all greenhouse gases. And that's all pretty solid measurements. These are back only 10,000 years, which is really where humanity really got going, civilization got developed. But then right at the end of it, in the industrial part of civilization, we have these spikes. The most beautiful piece of data in all of climate science, everybody agrees with this, is Professor Keeling in Hawaii started measuring CO2 on the top of Mauna Loa in 1960, actually a little before 1960. And that same measuring station, same location, has been just measuring it continuously ever since. You can see the rise of the parts per million starting at around 300, moving up to today of 406 parts per million. And the little ups and downs is the Earth breathing every season. Springtime comes, plants gotta breathe. So what do they breathe? CO2. And what do they exhale? Oxygen. So that's seasonal, and that's that beautiful piece of data. Okay, so where does it come from? Well, you're thinking coal plants, but how do we know that? It's very important to know where it's coming from. Well, we have circumstantial evidence of carbon emissions in the industrial age. So here's year 2000, there's 1850, and you can see that today we have coal, oil, gas, and cement contributing to the rate of emissions, not the accumulated emissions. Which countries or regions of the world is this coming from? Now we're getting a little peek on policies. Where are the buttons and levers to do something? You can see China coming up very quickly in the orange, the USA dropping off, European Union dropping off, India, watch out. It's ready to explode in an exponential manner. How do we know it's from fossil fuel generation? This is a plot from the year 1000 to the year 2000, CO2. It's the same plot. This is that spike again. But the yellow-orange is looking at those little bubbles in the ice and looking at not just the fact that there's a carbon atom on this CO2 molecule, but that carbon atom can have an atomic mass of 12, 13, or 14, carbon 14. There's a stable isotope of carbon, which is 13, 1 neutron heavier than regular carbon. what's interesting is that there's no carbon-14 in this stuff. That means it's older than around 20,000 years, because carbon-14 half-life will be spent out by that time. But biota, like trees, take up heavier carbon, carbon-13, at a slower rate than they take up regular carbon-12. Carbon-12 is what they like more. It diffuses through and does biochemistry better than carbon-13. It's a slight difference, tenths of a percent, but measurable. And this is the level in those little bubbles of carbon-13 over time, and look at it go down. There is very little carbon-13 in the air in those bubbles, very much less than the average in the atmosphere. That means that it came from living organisms at one time, but more than 20,000 years ago. There's other evidence, but forensics are closing in that this is from stuff that was buried, live stuff buried a long time ago that we call coal and petroleum. So we're putting the CO2 in the atmosphere, adding to what's already there. Where does it go? It doesn't all go to the atmosphere, only half of it. Some goes to the surface of the ocean, the first kilometer or so of the ocean, a quarter of it or so, and then a quarter of it goes into the biosphere, feed those trees. And yes, increased CO2 will help trees on the margin be a little happier, but there's a lot of other things that can happen that aren't so pleasant. So we looked at the atmosphere. We'll look at the oceans. First thing to ask is, how do we measure the temperature of the ocean? It's very difficult. Since the age of satellites, we've been able to put up satellites that image at various electromagnetic frequencies, from what's called millimeter wave, or a really high frequency radar, all the way up to the visible. And you can generate data about the surface of the ocean temperature through these satellites, and you get these humongous data sets. More importantly, in the last 20 years, there's been this incredible network of floating robots that are around the world. They're called Argo. That's the name of these robots. And some of this research in the southern hemisphere is centered in the University of Arizona. But this is a location of all these floating robots that measure ocean temperatures. And they do more than that. Also, they will take a dive down to 2 kilometers down, which is getting down there, and take measurements, pop back up again. When they break the surface, they send the data to a satellite, and you get this incredibly beautiful data set measuring the properties of the surface and the upper regions of the ocean. The surface temperature of the ocean is rising, as is as we'll see, the atmosphere. And this is the Brits, and this is just one chart of 100 charts that I could have shown in this area. There's 1850, 2000, temperature with a lot of variation is going up. The variations are due to things that have to do with ocean circulation. El Nino, there's other overturning circulations in the Atlantic and so forth. Sea level is rising. Now we're going back. This is the glacial age. So sea level is way down. Bering Strait is the land bridge. You can walk from what will be London to Paris, no problem. But as we get out of the glacial period, sea level rose and then leveled off in time for our Goldilocks period for civilization to develop. Let me zoom in on the modern era, which is just a tiny bit of this down here. 1880 to 2000. and a little beyond. You can see that the sea level on average across the planet is rising. And you can see the change is like 20 centimeters. That's that much, or this much, on average. In some spots, it's barely moved. In others, it's up a lot more than that. So these things are happening. The other change we notice in the atmosphere, in the ocean, is the acidification of the ocean. If there's more CO2 in the upper kilometer or so of the ocean, and it is an acid. So I think I learned that in high school chemistry. Carbonic acid, and if you drink Diet Coke or anything like that, you're consuming it quite a bit. The pH of the ocean, the acidity, starts out somewhat basic and goes down as carbon dioxide goes up. And this is now, and this is just curve fitting, what could happen in the future. But you get pH changes from 8.1 to 8 to 7.8, and you are changing the ecosystem of the ocean in a dramatic manner. Some positive and negative implications of that. Now let's move on to first of all, the oceans. This is something they don't tell you. And remember this. All that heat that's accumulating because we got a better blanket with more CO2 in the atmosphere. All that heat, very little of it's going to the atmosphere to make us a little warmer. Most of it goes in the ocean. And it's not going to go away fast. Remember when I talked about implications for hundreds, maybe a few thousand years of what we're doing? That extra CO2 we're putting in the atmosphere goes into the ocean, and it comes out very, very slowly, but it will come out. And we don't know how fast or how much, but it's going to happen, and it's going to influence the climate quite a bit. This is the amount for air, land, and ice. This is all you hear about. But oceanographers, people that really understand this, tend to be more concerned about the climate from what they're learning than the atmospheric people. You've all seen pictures of decline of glaciers and ice caps and so forth. This is the last 400,000 years, and it's just a pretty picture, actually. The point here is that we're plotting two things. The red on the left is the temperature from way back till now, and on the right is the carbon dioxide. The point here is that these two things are correlated. We don't know cause and effect. How does carbon dioxide in the atmosphere cause the warming through these glacial periods, or vice versa? We're pretty sure which way it goes, and there's some good evidence to explain that. There's your typical, ever been to Glacier? I mean, we've been to Glacier, and we could see it over the last 30 years. I remember when all this area we hiked on a few years ago was covered with ice 30 years ago when we were there. But that's just one glacier. Some glaciers are getting longer. Some are getting shorter. Got to look at data. And Arctic sea ice, everyone knows that last summer in the Arctic, there were temperatures of 50 degrees or more Fahrenheit. It was balmy up there. And when Princess Cruises gives you a cruise through the Arctic, you know something's changed. But let's look at data. This is the Greenland ice sheet mass and the Antarctic ice sheet mass. By far accounts for almost all of the fresh water on the planet. All the lakes and streams and other icy areas are insignificant compared to these two. And this is the mass change over time from the year 2000, we're not going back far now, to 2016. And it doesn't matter what the zero is, that's arbitrary. The fact is they're both going down, in very measurable, dramatic ways. Forensics marches on. Now let's look at land masses. This is the dynamics of land. We have the ocean, which takes in every year 338 units and puts out 332 units. Vegetation and land takes in 450, puts out 444, and a tiny little bit from those nasty coal people and cars. So why worry about it? Look at these numbers. They just swamp out that number. But remember, this system is tuned in equilibrium. And you just change one little thing, and the system wants to re-equilibrate. It's going to react. And the system says, a few degrees Celsius, what do I care? Civilization cares a lot. Okay, you got this? This is the first click through on how complex these 4 areas of our Earth's climate, how they interact, and things you got to worry about. But this is the first click. You can click through on any of these and get dozens and dozens of more blocks of dynamic elements in the system. It's really, really complicated. That's why there's so many researchers that are interested in finding areas that are virtually unexplored in climate science. So that's the simplified one. Now, to a scientist, or if you have children or grandchildren that are thinking of going into this just makes it exciting. This is an infinite playground for doing good science. Now, let's have some fun. The Earth's climate is technically called a complex adaptive system. It's a technical term. It means it's more than complicated. It's like chess, which is complicated, but it's chess where each piece gets to behave differently depending on what pieces are next to it. So you move your bishop across the board next to the knight, all of a sudden it has a different moving pattern. Try and put that in your computer and beat the world chess champion. Ain't going to happen. For complex adaptive systems like this, big changes never have a simple cause. If someone gives you a simple answer to anything in climate science, it will be wrong. Under transformations of the system, when the system gets kicked out of balance a little, you get extreme behavior. For example, extreme weather. Ups and downs, wetter, colder, hotter, cooler. All complex systems, when they're kicked out of equilibrium and they're seeking another equilibrium point, which may take a few thousand years in our case, there will be extreme behavior. You get more extreme behavior than you would at the set point. And finally, these influences, I think I've made clear by now, are a catalyst. A tiny amount of for example, platinum in a certain kind of chemical reaction will just send that reaction going crazy. And without any platinum, the reaction doesn't even happen. This is fuel cells in cars use that. It's a catalyst. It doesn't take much to set this system moving and seeking another equilibrium point. A physicist who's really good at statistics is going to have had some fun. What he did is he took some actual temperature data from a newspaper in a city. And we get these in the Star. You look at the back of the sports page. Once you see the basketball team losing, then you go over to the sports, the other side, and you see the chart. Well, this is all pushed together for many years. He took the average change out of it, so forget about the fact that there's an overall warming on the average. And he just readjusted it. And then he did statistical analysis. And he made some statements that are mathematically true about this data set. News. We're looking at this particular occurrence, that event, okay? That's hot. Recent heat wave was 71% natural variability and 29% global warming. That's a true statement on this little pretend example. On the other hand, he can make another true statement. Global warming increased the odds of the recent heat wave by only 0.25%. Well, it's not as bad as I thought. Another statement. Global warming has made heat waves like the recent one occurred 22 times as often as they would have otherwise. Okay. These are all true statements, mathematically right on. Watch out when you read headlines. You can't be too careful. Don't be a climate day trader. It doesn't work. You don't bring a ball of snow into the U.S. Senate floor and you say there's no global warming. There may or may not be global warming, but the ball of snow doesn't have anything to do with it. Another reason to be careful about statistics. This is the temperature over time, 1880 to the current time, just for a few years ago. And this is different groups are measuring the temperature. This was a piece of data that the scientists said variability, and people that weren't scientists that had a certain ideological agenda said, well, global warming has stopped. You average this out, you get a straight line. And that's it's almost 10 years. Global warming stopped. Well, the next year broke a record, 2014. 2015 broke a record. And 2016 broke a record. And put those on. The whole point is that those 3 records in a row don't mean anything either. You've got to look at averages over 10, 20, and 30 years when you're talking about how the Earth system is going to be changing with respect to that catalytic act of adding a few parts per million CO2. This is a report that just came out. It's so ironic. This is the best report I've ever seen by far on climate science. It's new. It's got the latest research. It's much better than the IPCC reports, that's a 2013. But not only is it old, but it's kind of not as good. This is put out by the U.S. government since the change in administrations. It is fantastic. Google it. Look at it. There's summaries. It's accessible. You can get at it. They have great summaries, executive summary, all the chapters. And a lot of the data I'm going to be showing now to make sure we're up to date is from here. Here's one of them. This is a more complete temperature measurement over time, 1880 to 2016. And you can see the trend there, along with the ups and downs. And there's reasons for those ups and downs. Climate scientists love that fact that this isn't straight and smooth. Here's what happens when you do 10-year averaging. Pretty clear. And this is meaningful statistically. The 10 years is actually probably a little short. So how do we know the climate is warming? Multiple strands of evidence. Snow cover going down, glaciers and ice sheets going down, land temperatures usually taken at 1 or 2 meters above the surface going up, air temperature near the surface, say when you're flying on a jet plane, the temperature of all the air below you is going up. Sea level is going up, ocean heat is going up, temperature over the ocean is going up, water vapor is going up, sea surface temperature is going up, and sea ice is going down, and there is solid data behind all of those. That's land surface, sea surface. It's all supported by hardcore data. And all of this data is fought over like a food fight. You can't get a, you can't get a conspiracy going in science unless you got one person. I mean, you have a conspiracy. I believe my own work. Nothing makes a scientist happier than showing somebody else is wrong or that the conventional wisdom is wrong. Einstein really enjoyed that part of his career. Another thing we can look at, which I don't have time to get into, is how computer modeling handles this. And computer modeling is challenging, incredibly challenging in this area. It's really gotten good over the last 3 or 4 years, much better. It turns out that computer modeling is actually easier in some respects than making really good measurement data sets on what you're modeling. So what happens is the data people measure some temperature distribution around the Earth or whatever. The modelers model it, and they don't agree. And, you know, people that don't understand things will say, well, then the models are wrong. Wait a minute. Maybe the measurements are wrong. Why don't we both work harder and see what happens? Those differences are what drives science forward. So there is that curve, and you and I got our fingerprints all over this, unquestionably. It's your fault. Projections. These are projections that are kind of, you got to make some projections with smart people, with computers and so forth, and you agree on a few scenarios, and you make projections. You don't know if they're going to be true or not, but this is the carbon emissions scenario. We can't know how much the Earth is going to warm if we don't know how much more carbon we're going to put in the atmosphere. And economists can't tell you that. If they can, you don't know about them because they're gazillionaires, because they can predict the economy. So they're scenarios, and that's what policymakers need to use. For a high scenario, in other words, we're going to go off like crazy as we have on CO2 emissions, a mid scenario, a lower scenario, and a Goldilocks scenario, which I'll have something to say about. And these are the temperatures that would be correlated with these between now and the end of the century, whereas business as usual, we're going up to 8 or more Fahrenheit average on the globe. Land temperatures go up a lot more than ocean temperatures. You don't want to be there. You don't want that for your grandchildren. There's a moderate scenario. There's a lower scenario. So these are the things that we have to do to make decisions, for you to make decisions. This is sea level rise scenario, just that little purple up there. And you blow that up, and then here's now, and here's these scenarios. Business as usual, Goldilocks scenarios, some mid scenarios, but they're all looking in the 2 to 8 foot range average across the planet. You're smart enough to know the implications, the immediate, proximate implications of that for literal effects, and the fact that, what is it, 60 or 70% of the population of the Earth lives within so many miles of an ocean. Ice extent, we have different scenarios, most of them going down to 20% or less of what we have now, and a lot of them going to zero ice, zero Arctic sea ice in the summer, and by 2050. Surface pH, you got a Goldilocks scenario, a worst case scenario. So we do these for all of that. Now, what I haven't talked about yet are really frightening possibilities. When you got a complex system, you don't know how it's going to respond. You can put these averages in. It's kind of business as usual, and we can follow the computers, and we can go. But there are some events which are due to things called feedbacks, which can come out of the blue, like a earthquake on the San Andreas Fault. You know it's coming, but it may be 20,000 years, it may be tomorrow. So you cannot predict them. But these are things in the climate where there's good reason to do a lot of research to understand more, because much more dramatic things can happen than any of the projections I've just given. So El Nino, Amazon rainforest, you can have catastrophic effects in this with feedbacks that really affect the climate. Permafrost, methane hydrates, don't have time to go into that, but you can have some, effectively a bomb of CO2 coming from Siberia, Alaska, and northern Canada. Boreal forest, same thing. Arctic sea ice, it's already happening, the feedback there. And some others. So these things also have to go into any kind of planning or policy viewpoint as to what we should do about it. Extreme weather events. This is data, not a projection, up to 2012. They're going up, and they will continue to go up. But don't ask me, did Hurricane Harvey, was that caused by global warming? To me, that's what mathematicians will call an ill-posed question. It's just, don't ask. It's getting back to those 3 headlines I talked about. OK, consequences. This is just an overview of the consequences. Average temperature rise, regional climate shifts. As Jerry said, Arizona will get drier and hotter, and there's reasons for that. Areas that are wet will probably get wetter and so forth. Regional ocean warming and acidification, sea and ice reduction, sea level rise, and so forth. Those lead to proximate effects. Flooding, droughts, disruption of agriculture, extreme weather, and effect on species. Secondary effects are where you're getting a long way from science now. Wars. Certain writers like Jared Diamond and others can look at wars as being often caused by climate or resources that might be imperiled by the proximate effects. Human disease increase. There's work going on at the University of Arizona on this. Clean water shortage, food scarcity, economic disruption, population displacement. Woe is us. So what we have here is a global commons. And whether you like it or not, regardless of your political affiliation or ideology, the seas and the atmosphere belong to all of humanity. But the lands belong to sovereign states. This is the nub of the problem. And we're a sovereign state, and sovereign states probably are pretty good to have around. One of the things that's happened in 2015 was the IPCC and COP21, where the countries of the world came to agreement. They at least agreed that climate change is generated by humans, and we've got to reduce fossil fuel emissions. I mean, just getting everybody in the same room to say that was a huge accomplishment, I think, having a lot to do with John Kerry. Not too much to do with anyone else on that screen. It's a remarkable diplomatic achievement. And people talk about what it didn't do, and that's what I'm going to do right now. But at least we got together, and we're saying each country has a goal to reduce emissions. So they agreed that the goal is, given these computer projections, that's all we got. We're going to keep below 2 Celsius, above the 1880, 1850 levels. It'd be even better, cooler, to do 1.5 Celsius, and we want them to peak. In other words, we want to see global emissions, the rate of emissions, go down very quickly, and rapid reductions thereafter. And every country puts together a climate plan. And then you come together and talk again and check it and so forth. It's all voluntary and so forth. However, these are diplomats. The scientists were there, but a lot of the science got lost in translation when you got to the political documents. That's normal. There's a bubble that they were living in. And some of us are not happy about it because it was a good thing to get everybody together, but we're kidding ourselves that we're making progress. And here's why. For example, this is global emissions. And here's business as usual. This is this Goldilocks emission. And this is the current intentions of the countries to go up to there. And you're still above 2C. And since then, no one's come close to their intentions. So we've got to do more. The dirty little secret, which really good climate people are really not happy about, is that goal, getting to 2 degrees or 1.5 degrees, what they had to do was they had to fix the books, they cook the books. They had to say that at some point we're not only going to reduce carbon dioxide emissions, but we're going to go negative. We're going to somehow have less carbon dioxide in the air every year than the year before. There's technologies that are looking at that very early stage, but that wasn't out front. That was kind of the guy behind the curtain. So there had to be some negative here because we had this humongous amount of emissions that accumulate and accumulate, and they're still accumulating to this point. It's like saying in 20 years from now we're going to balance our budget, but there's 2 ways to get there. One is to balance it a little better, closer every year. The other is to spend like mad, and then the year before 20 years, in year 19, we balance the budget. Well, those are 2 different fiscal and financial situations. Well, there's 2 different states of the atmosphere depending on how fast we get emissions down now. And we're not doing it, and that's why some people are so upset. I'll cut through this. My hero, one of my heroes, is Jim Hansen, whom I have had the pleasure of meeting and having some of these discussions with. He was at Paris, and he's the guy that really testified before Congress in the 80s that there's a problem. He was, Jeremiah. And this is his comment on the celebrations in the Champagne in Paris. Shameless, pre-planned backslapping accompanied by an accord that guaranteed nothing except continuous high fossil fuel emissions. It created a comfort zone, like, oh, we got together. But if the people that are emitting, the people meaning the companies or the countries, aren't uncomfortable, we're just increasing that cumulative CO2. So this is a chart which is 1900 to 2100. This is now, this is temperature, and these are these 3 scenarios, okay? What I'm going to put on this is the best estimate for where we'll be in 2100 by what I consider to be the best scientists that should be talking about that. And it's right here. 4 to 7 degrees Fahrenheit. Could be a lot more if some of these feedbacks happen. Could be less. The models could be a little wrong, or we could be reducing emissions by some magic way faster. But that is catastrophic in terms of the change to the infrastructure of the civilized world as we know it today. Now here's what excites climate scientists the most. It's what we don't know. High and low altitude clouds. If I were going into climate science, that is such a tough question. That's where I'd want to work, and you can get lots of data too. Effective aerosols that we're putting in the atmosphere like mad from cars and transportation and from electrical utilities. Those are very, very complicated. I've done some work in that area, and they actually have a net cooling effect on the atmosphere. Dynamics of the ocean, just beginning. We've only scratched the surface. Ice shelf feeding sea level rise. There are some potential catastrophic effects that Jim Hansen has written a paper on. Don't know if it'll happen. It's like the big one in San Andreas Fault. And climate sensitivity. This is a term that says if you doubled the CO2 at any given point now, how much rise would you get over 10 or 20 years and then ultimately over 100 or 200 years. And that's a number that we like to argue about and discuss. It's kind of a figure of merit. So those are just a short list of the things that are really keeping us in the business of trying to get more understanding and more explanations of the data we see. Now, we can adapt or we can mitigate. We can also do nothing, or we can geoengineer the atmosphere. I don't want to go to either one of those two, but we're going to talk a little bit about this stuff. The climate science uncertainties I've just talked about are well defined. The uncertainties are scientific statements themselves. I'm comfortable with that, and there's something we can do about them. Research, more data, more models, more smart people digging into that. But that's a small part of the challenge you face. What are global emissions going to be by 2050? Nobody knows that. That's an emergent reality. It becomes real year by year. The big one for me is technological innovation. As the climate starts talking more and more to us that this is going to be an inhospitable world for our infrastructure, technology and technologists will respond by getting clever and identifying problems and solving them, whether it's from carbon sequestration to much more efficient energy utilities and so forth. This is where I put most of my hope. And of course, energy and climate policies are going to matter. Remember in mitigation that most of the growth of carbon dioxide is not in the first world. It's not in our world, OECD and the United States. It's in the developing world. India and China are the primary ones, but it all adds up. So this is where the increase is. The developed world is on a trajectory to reduce emissions and continue to reduce them. I got to just say a real quick comment about coal. You know, there's sometimes you don't know when someone's talking about a certain business or something. You aren't sure, do they really believe what they're saying, or are they, you know, is it a gratuitous remark with an agenda or whatever? Coal has problems. Air pollution, water pollution, these particulates, aerosols, and black lung disease and so forth. Environmental destruction. And, by the way, it's the worst thing there is for CO2 in terms of amount of energy generated in a utility. So I call it the canary in the coal mine, but we're in the canary's cage. We're not looking at it. And it's not the coal mine, it's the coal industry. So I'm breaking from my science talk for a moment. This is just too blatant. World Health Organization in 2008 has good epidemiological data on the fact that there are 1 million deaths a year in the world due to pollution from coal. How many from nuclear energy per year? Average 1. Solar. How many from, well, solar has more actually, but it's still a small number. 1 million deaths, and it's rock solid. You know why these people are dying. You know where it comes from. So I just can't abide anyone saying, in the United States or in the developed world, saying we should do anything more with coal because we have options and alternatives. Combined cycle natural gas, nuclear, wind, and solar.
Wash the coal first.
Clean coal. There is some coal plants are much more efficient than others, and there are scrubbers that really do a good job. The U.S. per capita is a much smaller contributor to those million deaths than any other country because we do have better coal in, plants, but it's still unacceptable. Since our last meeting, 1 gigaton from the planet. Make that more real, that's in pounds. Just since our last meeting. It's going on. Doesn't matter if people are talking in Paris. We have to do something. I don't have any easy answers, but the IPCC is an important nexus globally. And by the way, there's only one country in the world that isn't a member, or won't be a member in a few months. I forget what that country is. Treaties. To me, here's the big one. Provide technological options. One of my jobs is consulting with an investor on nuclear energy. And Indonesia is one of the places that's being looked at. We want to give the president of Indonesia an option when he must create gigawatts more power over the next 20 years for his country. And I want to give him an option that isn't coal, because that's what he's going to do without any other options. But that goes not just for energy generation, it goes for energy efficiency and so forth. Moral suasion by leading global powers and financial incentives. U.S. has a pivotal role in this. We are good guys today in all of this in terms of reducing emissions, providing technology, and so forth. So our engagement with the world through the IPCC or any other body is important. Climate science research. I really think we've got the best climate science establishment in the world. The Brits, the Chinese, the Germans, to some extent the Australians and others are in there. But we are leaders, and we have to continue to lead because scientific understanding is the ultimate answer. Eliminate coal. If you haven't got something better, use natural gas, which the U.S. is doing. Clean technologies, nuclear, solar, and wind. I could give a whole talk on nuclear plus solar and wind. It's a great combination. Electric vehicles, for a variety of reasons, are one of the keys, and it's not because they're quiet and they don't emit anything. It has to do with energy policy. Improved energy efficiency is the ignored crazy uncle that lives upstairs. Is really a significant contributor to reducing the energy intensity of the United States and much of the developed world and the developing world, because energy efficiency of appliances, they get sold right into the third world because they come from China or the United States or whatever. And a carbon tax. And this is a plug for our group who works with the Citizens Climate Lobby. They're will be in our lobby here after the talk. This is to me, is the cleanest, most simple, non-ideological, non-partisan approach to really making a global dent in the rate of emissions and trying to get that to turn over as quickly as possible. Take a piece of paper from them, talk to them at the table, and make up your own mind. Some more good news. COP23 just was in Bonn, Germany. Canada and Mexico have joined a coalition of not the United States, but 15 states of the United States, including these states, to resume leadership in doing this climate mitigation. EU, China, and California, that's 3 great countries, right? Announced they will step up cooperation on carbon markets. And 25 national and subnational jurisdictions have signed on to the UK and Canada's alliance to phase out coal. If somebody's phasing out coal, that just tells me that that's a place where policies are somehow getting to ground and doing some good. That's that canary. More reasons for hope. Rapid advances in climate science. To a scientist, and there's scientists in this room, ultimately, that is the most important thing. It's going great now. We got to push it faster and harder. Emissions are leveling in the US and EU. China is smarter than you might want to think, and we have to deal with them in some of the companies I'm on boards of. And there's some interesting, good things happening in China in terms of technology and policy. Reduced energy intensity, wind and solar. Advanced nuclear is, to me, the #1 20 years and out answer when combined with solar and wind. Coal is declining, and public support is growing. So there's a lot of good news. What if it's a big hoax and we create a better world for nothing? You can't lose. I mean, how could getting rid of coal be anything but good? So, thanks for your attention.
Explain the difference between emissions. Is this working?
Is it working?
Hello?
Yeah. Okay.
Could you explain the difference between emissions from metallurgical coal versus coal used for power plants? We have a lot of metallurgical coal in British Columbia. Do we have to shut all that down?
What do you mean by metallurgical coal? Do you mean
used for making steel? We export a lot of it to Korea to make steel.
Coal, if you burn it.
We can't hear you very well.
If you burn it, if you burn coal, it contributes. It doesn't matter what you burn it for, and lignite, and a lot of the Canadian coal is some of the dirtiest coal that we have on the planet. So coal's just, I mean, we're going to need it, but we only need perhaps 0.1% of what we've got. And we can use the carbon to make polymers and make stainless steel and so forth.
Yes, sir. Is this on? I can't hear. Hello? Is it on? Can you hear me? Okay, I can hear it now. You said early in your talk that the temperatures and the carbon dioxide were correlated, and that you weren't sure which caused which. I'd like to follow that up with a question. Have you considered, and are you aware of the connection between the Earth and the Sun, and it's the electrical connection between the two bodies, and more specifically space weather, as you know?
The question was about the fact that we have a correlation between CO2 and temperature over 800,000 years. Does it have much to do with space weather? And by and large, no. What it does have to do with is the orbit of the Earth and how that is wiggling around in 3 different ways. And we're getting more or less sun over a certain 100,000-year cycles. And it's felt that that is one of the contributors to these glaciation cycles, which we don't fully understand. The amount of sun right now is going down over the last decade or few decades. So that's a net cooling effect, but it's a very small effect compared to these other drivers.
I have a couple questions. I was wondering how forest fire, the carbon dioxide that's emitted during forest fires compares with other forms of emission.
The question was, how does forest fire CO2 emissions compare with other kinds of emissions? It's measurable, but not a major factor. It could become a major factor if they get much more extensive by a factor of 3, 4, 5 or more.
And the other one is, the population of the Earth is anticipated to be like 9 billion after some time. It seems like with that kind of population growth, the world political climate becomes more conservative. And how does that, and then along with that comes an increase in denial. How does one deal with that, or is that really a factor?
That is beyond my scientific capability and competence. But yeah, governance issues, they've always been. In the last 10,000 years, governance has always been critical. They'll continue to be so. We're probably going to taper up into 9 billion people from around 7.2 right now.
Hello, I'm a member of the Pima County Board of Health, and I wanted to share with the audience, and I'm sure you're aware and many are aware, that the health impacts of what is happening with the climate are truly significant. Aedes aegypti mosquito is already in Pima County. Hemorrhagic dengue is in Hermosillo, south of the border. It's moving in this direction. So the health impacts as the climate warms here is not a trivial issue. But more in your zone, I'd like to ask you about methyl hydrates and how that will affect one of those positive feedback potentials.
You mean in the Arctic?
In the Arctic, yes.
Well, there's two sources. The permafrost and swampy areas in the high Arctic across the globe have in them a tremendous amount of carbon, much more than is in the atmosphere today. That's, by the way, if you're a geologist, you see that stuff moving around over hundreds of millions of years. But as the snow melts, the permafrost thaws in the summer, and you get bacterial operation, and that emits methane and CO2 to some degree, and that contributes to the atmosphere. It is a very vanishingly small effect right now, and can't grow that fast. The best scientific evidence I've seen is that that could be an issue, but it's not really a time bomb issue over the next 100 years or so. But it is an area of active research.
I wonder if you talk for a minute about advanced nuclear and kind of what you think. Obviously, that's a big topic, but can you give us just a little flavor of what you mean by that?
Yeah, I don't want to get into an argument about it because it's all emotion. I am working to develop small modular nuclear reactors and try to get them fielded somewhere other than the United States because it's impossible to do here. Basically, the nuclear plants that we have in the United States, there are 99 of them right now, are obsolete dinosaurs, and they were developed during the time when you bought an Apple IIe. That's the technology that people are saying is bad, and non-proliferation problems, and it costs too much, and it's too dangerous, and all of that. There's advanced nuclear technology that has been developed, and just like you're not going to go out and buy an Apple IIe right now, you want to buy good technology in nuclear. There's tremendous technology. One of the primary investors of this is Bill Gates, and he, like we, my group, went to Washington and tried to get some glimmer of hope of doing something new, and Bill Gates gave up and went to China. That's where he's going. And he's smarter than I am. So we're looking outside the United States as well. It's safe. It's 30 times more efficient than current nuclear. It has very little long-lived isotope waste. And it's going to be competitive to coal and natural gas. It's going to be a long road. It's going to be 15 years at the earliest before that stuff gets going.
You always hate it when, can you hear me?
No. Closer.
Very close.
You always hate it when someone comes and asks a question that you know you haven't talked about or haven't covered, but I'm going to break that rule because I think I enjoyed your talk hugely when it comes to the science. But what I think is missing, and this is mea culpa, is how do we explain where we got and what can we do about it? So I'm not hearing much about the economic system, and which one of our members boldly referred to recently as capitalism. Hello, that was Murray, I believe. And then you decided you didn't want to talk about ideology, but surely ideology has to figure there, and this is where I'm being unfair to you, probably. But historians, of which I'm one, this is their stock and trade explanation, and you know, we can have multivariant explanations. That's fine, but we should at least allude to them and tackle them.
We have the code for
Repeat the question, please.
The question?
No, the speaker who's got a mic that works.
Yeah.
We can't hear your mic.
I can't paraphrase it. It had to do with going beyond the science and looking at what we can do about it in the real world.
Yeah.
Of politics and policy.
He said it better than I could.
And the best, most unambiguous step that my wife and I know is citizens' climate lobby. Mm-hmm. When people ask me, what can I do? That's where I start them. There are a lot of other good things happening, but that's number one for me.
Thank you.
Yeah, I understand that for the Hayden Planetarium out in New York, that we're coming into a cosmic orbit where we were about 240 million years ago, which was a warming period that lasted for a couple of million years or so. And at the end of it, there weren't any ice, I understand, at the poles. Now, how are you factoring this into the global warming?
Those effects that, if you look back, I'll try and paraphrase the question. On timescales of 280 million years or so, there's been warming trends and there's been cooling trends before that. This is an active area. This isn't neglected at all. And most of those trends, all of those trends happen on a 20,000 year to 20 million or more year time scale. We are talking about a moment in time on those scales, and our problems are going to be happening on the decade and a few hundred year scale. And those other effects that might involve changing the climate are going to be much too slow to have any significant impact on it.
Well, I understand that for the past 18,000 years, like the Atlantic Ocean has been rising significantly. For a study by paleontologists that was published in December 12 of National Geographic.
I think Yeah, without getting into an argument, I think I covered that. And coming out of the last glacial minimum, the sea level was down like 100 meters, and it has been rising, but then it leveled out. And what we're seeing is a rather rapid rise that is highly correlated with CO2 emissions and with without any other good explanations that we found. So that's all I can say.
I just have one more. Is there a future for thorium-based nuclear reactors?
Another nuclear question. I should come back and give a talk on nuclear. The question was thorium-based reactors. There's nothing special about thorium. Thorium, uranium, plutonium. Thorium's, it's good, and some of the advanced reactors are going to be capable of thorium reaction. It's cheap and it's rather safe. But they're starting out with uranium because it's readily available. So it's just a switch out. It's part of the future. I hope we get to, I'd love to be in a position to have to make that kind of decision on a real reactor.
I've seen some statistics where the oxygen level is lower. You know, you keep talking about the other side. I'm more worried about where's our oxygen level that we breathe, and I didn't see any mention of that.
Okay, is the oxygen level lowering, and is that an issue? CO2 is in parts per million. Oxygen is what, 18% of the atmosphere? It can go down a lot. In fact, go to the top of Mount Lemmon, and it'll be down. And so it's not foreseeable that any oxygen levels that would have to change by from 18 down to 10% or something. There's no evidence that I know of where anything like that is even plausible. So breathe easily.
It takes a lot of trees to make that much oxygen, and we're burning them down.
One more reason to not burn them down.
I'm not even sure how to formulate this, because basically what you showed us was a system that's so complex that even in various areas geographically we have microclimates, and there's no way we actually have somewhat cataloged them. But to review how all those interact with each other to create the whole. But basically, my question is about the trees and the oxygen. Trees, you said their optimum carbon is carbon-13.
Carbon-12.
Carbon-12, okay, I'm sorry, I misheard. And that they are now getting a different type of carbon atom. But that being said, in this broader system, what I think I heard you say is that even the solar light spectrum that they are receiving is shifting, which is probably changing that atom somewhat. And I'm wondering, the lungs of our planet have always been trees. And I'm wondering if we are now even receiving a radiated type of carbon since the shift. Is that more of a...
Okay.
And so therefore we're living in a more highly radiated environment.
You can rest easy in that regard. The amount of carbon-13 is a fraction of a percent, these changes. They're more indication or indicia of where something came from. And but you're right about the fact that regional effects can be completely different than the average. And there's several people there's a center at the University of Arizona that's looking at Southwest effects. And what they do is they pull all the research from all climate science and then try and focus what can we learn about our origin, our area of the planet. And all groups around the world are doing that, especially those that are near sea level, like Indonesia, Melanesia, and so forth. Those are problems in and of themselves because the averages really don't tell you what to do.
Well, one of the problems we do have is our trash. And between Japan and California coastline, there is an island that covers the sea surface. You're saying it's like a blanket. And it's not the cause, but it definitely is a contributor to sea warming. And I think they said it's the size of Rhode Island. So, and a lot of that came from, unfortunately, the Fukushima, I think, nuclear reaction.
There's a whole topic of the health of our oceans. Yeah. The only thing I touched on here was the acidification due to increased CO2. That's what all we're covering. Any other questions?
Could you tell us a little bit about seeding the atmosphere with sulfur? Is the research being funded sufficiently? What are the chances that's going to work? Clearly, human beings and our governments are not going to deal with this in time.
Okay, the question was geoengineering, trying to manage the weather by, for example, putting sulfur into the stratosphere or iodine and so forth. There's work going on small scales on that. I think it's very long term, 50 years and out, and it's an experiment I don't want to be around to happen along the line. Someone said it's trying to mess with the upper atmosphere to change the weather. It's like finding a new biomolecule that had efficacy in rats for one kind of disease in a preliminary test. And then you want to inject every human on the planet with it and see what happens. That's what geoengineering is. Unintended consequences are, you better be, I don't know how you can be sure you're right on that. We are, by the way, we are geoengineering. It's called CO2. Yeah. It's fossil CO2.
It's happening right here.
Unintended consequences. What we're living with.
So we've been watching the planes over in Marana. We're about 2 miles from the Evergreen Airport. It is actually happening here in Tucson, geoengineering. Just so you know, please research it. We're watching it happen. We're about 2 miles from the airport, the Evergreen Airport in Marana. I've got lots and lots of video and photos, if anybody would like to see them.
What do you think they're emitting?
Oh, they're definitely making clouds. I don't know what it is because I'm not at the airport. I don't load the planes. But I would like to know what it is. Do you have an answer?
You're talking about these apparent streaks of clouds behind high-flying aircraft?
I'm talking about fairly low-flying aircraft making lots and lots of grid patterns and then forming clouds.
Well, there's more than one reason why aircraft can create condensation, which is what clouds are.
Okay, well, what we watch is a lot of airplanes going back and forth, making lots and lots of grid patterns, and then they form clouds that cover the sun.
Okay, well...
We're actually watching it happen. So like I said, I have video and photos.
Okay.
So it's actually happening.
Well, I haven't seen the data, so I can't comment.
So nobody's testing the air. There's whatever it is they're putting up there.
To my knowledge, no one is attempting to do geoengineering. There were some attempts to do it in the 60s and 70s.
Okay.
Which didn't work too well.
Would you like to see the video footage that I have?
I think I've got enough on my plate. Thank you very much.
Yeah, let's give you a big hand. Okay.